Hi friends, in the last video we've seen how EMF induces in a circular loop when it is subjected to change in magnetic flux. In this video we'll discuss Lenz's law, which gives us the direction of that induced EMF. The Lenz's law simply states that the polarity of induced EMF is such that it tends to produce a current which opposes the change in magnetic flux. In simple words, your current should oppose the change in magnetic flux. Got it? Now take this example. When V is 0, when you don't move a magnet, there will be some magnetic flux through it, but it's not changing. So here no EMF is induced. When you move this magnet towards this coil, when you move the north pole of this magnet towards this coil, what happens? The magnetic field is increasing. Got it? So the induced current should decrease the magnetic field. The induced current should produce a magnetic field in this direction to, to, to oppose the change in magnetic flux. So what current can give magnetic field in this direction? This one, right? So the induced current is in this way here. Got it? Similarly, here if you take the magnet in this direction, if this is the velocity, here it is given. Okay, now here the magnetic flux is decreasing. Got it? So your induced current should be such that the magnetic field provided by that induced current should be in this direction, should increase so that it compensates this effect of changing magnetic flux. So your magnetic field that is given by the induced current should be in this way. Which current can give that? If the current is in this way, right? So this is the direction of induced current. Got it? Now there is a smarter way to get this direction of currents, induced currents. Say you have a magnet here and this is your circular loop. First of all, if I move this magnet in this way, what happens? Magnetic field in going into this loop increases, right? So my induced current should be in such a way that it opposes the change in magnetic flux. It opposes the change in magnetic flux. So to get the direction, you observe one thing. Once current is induced in the coil, it gives magnetic field lines, right? And you know that magnet also gives magnetic field lines. So this current carrying loop, after the current is induced, the current carrying loops is simply acting like a magnet. It's giving out magnetic field lines, okay? And so if I say that that loop is acting like a magnet, that should have some poles, something called as north pole and south pole, right? Actually, one face acts as a north pole and other face acts as a south pole. Observe one thing. Say if you have a current carrying loop like this and this is the direction of current, what happens here? Magnetic field lines go into the screen here and come out of the screen here outside, okay? Now see here, if the direction of current is clockwise, as you see from this side, then what happens? Current magnetic field lines are going into the screen, right? So you know that magnetic field lines come out of a north pole and go into a south pole, right? So what happens here? This side of the loop, the side which you are seeing, that face, it is acting as a south pole. You got it? When the current when the current direction is clockwise in a loop, it acts as south pole. And similarly, when you see the loop from the other side, what happens? There it is anti-clockwise. You see that the current is in anti-clockwise direction, and when you see it from the other side, you will feel that magnetic field lines are coming towards you. So that is nothing but north pole, or acting like a north pole. So the phase in which the current is in anti-clockwise direction, that acts as north pole, and if the current is in clockwise direction, that phase acts as south pole. If a north pole of magnet is taken towards a loop, this obviously changes magnetic flux, right? So this induced current should oppose the change. So when can it oppose the change? If this phase acts as north pole, then what happens? You know that like poles repel each other, and hence it will oppose this motion. So this should be North Pole, right? What does it imply? It implies that if this should act as North Pole, the current should be in anti-clockwise direction. That's it. Here you got the direction of current. And take another example. If you have a loop here, if your magnet is taken away, again the induced current should oppose this magnetic flux change. So when can it oppose? North pole is going away. So if this should stop this motion, it should attract it back. You know that like poles repel and unlike poles attract, right? So if this magnet, this circular loop should attract this north pole, when will it happen? If this face acts as south pole. That's it. So you know that when the current is in clockwise direction, then that face acts as south pole. Hence, here you got the direction as clockwise. Now there is a way to remember this clockwise and anti-clockwise senses. Write n in this way, and here you have these arrows, and write s in this way. Put arrows here. From this you can say that here the current is clockwise and it acts as south pole. Here the current is in anti-clockwise direction. This acts as north pole. This is just a way to remember, and hope everything is clear till now. Observe one thing. Person has to do work in moving the magnet, because always the induced EMF or induced current tries to oppose the motion. So you have to spend some work in moving the magnet always. And this energy, where does it go? This energy is dissipated by the Joule heating produced in this circular loop. Current is going right, so some heat is produced, and the work which you do in moving the magnet is produced as heat there. Got it? Take this problem. You have a constant magnetic field all over this area going into the screen. Okay. Now I want to bring a closed loop of some random shapes here. I want to bring this closed loop in this way. First, my velocity direction is in this one. First, it enters this area, and then it moves through this area, and finally it comes out of this area. Okay. What happens here? First, when it enters this area, magnetic flux is changing, right? It is something like magnetic field lines are increasing into the screen. First there were no magnetic fields here. As it passes, as it enters at this area, what will be the direction of current? Here what is happening? Magnetic field lines are going into the screen. So my induced current should oppose that. So it should give magnetic field lines coming out of screen. When will it happen? If current direction is this one, then I'll get magnetic field lines coming out of the screen inside this loop. Okay. So at this region, when the loop crosses this line, my induced current will be in anti-clockwise direction. And when the loop is moving through this region, what happens? Nothing happens, because magnetic field lines are not changing. So flux is not changing, so no current is induced. And what happens here when it's coming out of this region? So there the magnetic field lines are decreasing, right? Decreasing. Those magnetic field lines which are going into the screen are decreasing. So my induced current should increase them. So when will it happen? If the current direction is in this direction, or if the current direction is clockwise, that will do it. You got it? We'll solve some other problem. Say I connect a parallel plate capacitor here with the wire. Okay, two plates of this parallel plate capacitor with a wire. I am bringing the north pole of magnet towards this loop. Okay, what happens? Obviously flux is going to change, and hence some current is going to induce. Current is nothing but just the movement of charges, right? So obviously some charges will get accumulated on these plates. Now I want to know which plate gets the positive charges and which plate gets the negative charges. Observe this. North pole is going in this way, going towards the coil. So the induced current should oppose that, right? When will it oppose? If the current is in this direction, because magnetic field lines are increasing in this way. So my induced current should give magnetic field lines in this way. So this should be the direction of my current. And what does it mean if current is going in this direction? If current is going in this direction, this plate should get positive charges and this plate should get negative charges. Okay, now take the same problem in this way. You have a parallel plate capacitor. I'm bringing two magnets and two north poles towards the coil, one from here in this way and another also from here in this way. Both are coming towards the loop only, but from opposite sides. Then what happens? How to decide the plate which gets the positive charges and that which gets the negative charges? Here it depends on the strength of the magnet. The magnet which is stronger will dominate the effect. So if this first magnet is stronger than the second one, then the result will be same. You get current direction in this one, so the upper plate gets positive charges. Or if this magnet is stronger than the first one, then the result is what? Reversed. That's it. Hope you understood the concept. Let's move forward. Let's end this video with eddy currents. Till now we have studied electric currents induced in well-defined paths of conductors like circular loops, rectangular loops, etc. But when bulk pieces, say a plate or a cube or any bulk material, if these bulk pieces of conductors are subjected to change in magnetic flux, then currents are induced in them also. Of course, here since you don't have a specific path, the induced currents are something like this, some spiral, or they are like eddies in water, and hence they are called as eddy currents. Actually, these eddy currents are undesirable because wherever you have, say, a coil which is wounded with a metallic core, these kind of arrangement is used in transformers, electric motors, etc., and many machines. Okay, whenever you have such an arrangement, these eddy currents, what they do, they just heat up the material, and energy is dissipated by this Joule heating effect. So this is undesirable, right? What can we do to reduce this? Note that the magnetic moment that is induced for these eddy currents will be current times area. I said this before. Okay, so it is dependent on the area, right? What we can do, if we can reduce the area, or if we can give less area for the eddy currents to move around, we can considerably reduce this effect, heating effect. So wherever you have a plate, you can use this arrangement, use some slots or holes or any something like that, just to reduce the area. Here you have eddy currents moving like this. Here, since there is less area, it will be like this, and hence the magnetic moment will be less, and hence the effect can be minimized. Of course, when it comes to bigger machines like transformers and motors, we have many modern techniques like they laminate the metal core with some insulating material so that the heating is reduced, and we have some techniques like that. However, hope everything is clear till now. Let's end this video and keep watching. Bye.